Hey guys, welcome to section 7.4. I want to go through dealing with inequalities and systems of inequalities. You'll notice on some of these that I had already done some of the work on this because I got most of the way through the video and then lost it, so I'm starting over. But so some of my work is kind of still here from my first attempt at this video. So let me go through what we're looking at for this one. So when we do graphs of inequalities looking like this, this should be reviewed to you guys. You've actually done this as early as Algebra 1. You did it again in Algebra 2 when you did systems of equations. So a big chunk of this should look familiar to you guys. But let's go through some review on this. If I give you the equation that y equals negative x plus 4, I just said graph it, right? You would be graphing a line. Y-intercept is positive 4, and you would be going down 1 over 1 for the slope, right? And so that's where they got the line that you see here. The two extra pieces that come in when you're doing inequalities are whether your graph should be solid or dotted, and that's based on whether or not you got an equal sign, right? So because there is an equal sign involved, that's why the graph is kept solid instead of dotted. If there's no equal sign, if it's just less than or just greater than, then we do a dotted graph. The second part is shading, right? And so you can see where I shaded on this, but basically there's two ways to figure out the shading, and I'll kind of tell you which method is best for which situation. For the most part, if I said that we are looking at the range of answers for y that are less than or equal to this line, right? Well, here's the line, right? Here's where it hits the y-axis. So where are the y values that are less than that line, right? That would obviously be down here. So there's only two places you can shade this graph, right? It's either this area down here or it would be this area up here, right? So because it says y is less than, I want to shade the y values that are less than my graph, which would be down here. The other way you can figure out the shading is by picking a point, such as 0, 0, plug it in for x and y, and then determine whether or not the statement is true or false. If it's true, then the point that you picked should be in your shaded area. If it was false, that means the point that you picked is not in your shaded area, and you would shade the other side. So if I were to pick the point 0, 0 and plug it in for x and y, well, 0 is less than or equal to 4, so it's a true statement. So therefore, I know 0, 0 should be in my solution set, and therefore I want to make sure it's in my shaded area. That's just another way of looking at it. There will be a need for that on a future graph, but let me move on to our next step here. So we're going to look at shading a quadratic. So a quick reminder on, first of all, just graphing the quadratic. If we had 2x squared plus 1, right, we know that we are taking the parent function, which would have a vertex at 0, 0, shifting it up 1. So you can see this graph was shifted up 1. And then what would that 2 in front do to your parent function, right? It's positive, so I know it's going to open upward. And with the 2 in front, I know I'm going to get that vertical stretch of 2, right? So do keep in mind something we addressed earlier on in the very beginning of the year when we did all these transformations and we talked about vertical stretches and shrinks and horizontal stretch and shrink. Remember that a vertical stretch is really the same thing as a horizontal compression, right? If you stretch out a graph vertically like this, right, well then naturally it's also going to close inward as a horizontal compression. Typically it's easier to see it as a vertical stretch because it's a little more straightforward of a process. Anytime this number is bigger than 1, you get a vertical stretch. If it's less than 1, then you would get a vertical shrink or vertical compression. So anyway, that's the graph that we had. Of course, you could use Desmos or a graphing calculator to see that graph if you had questions. You could even go as basic as just plugging in some points and plotting them and then drawing your curve through those points, right? We can always fall back on that super basic method of doing this. I know it's solid because there was an equal sign involved. And so that's where the graph came from. So let's look at the shading. Where are the y values greater than the parabola? So let's look at where it hits the y-axis. The y values that are greater than this would be right here, right? And so that's where I determined to shade the inside part of the graph rather than the outside part of the graph. Because again, there's only two places you can shade. It's either inside the curve or outside the curve. So with this one, again, if you weren't sure, again, remember the other method is pick a point like 0, 0 and plug it in. So if I plugged in 0, 0, well, 0 is greater than 1. That would be a false statement, which means 0, 0 is not in my solution set and it should not get shaded. And that would tell me I had to shade this piece instead. So different way you can look at it. So if you want to try one of those on your own here for practice. So again, this was one, sorry that it's already filled in, but I had already done this and then lost the video, so I'm on my second round here. So remember with this one, again, it's a graph that's been shifted down 1. So that's why I shifted my vertex down 1. The negative 2 that's in front is going to do two things to it. The negative will cause it to open downward. And the 2, again, is that vertical stretch. So I'm going to get basically a skinnier graph than my parent function would be. I kept this one dotted because there's no equal sign. And then again, as far as the shading goes, if y is greater than the parabola, so here's where I hit the y-axis. Well, where are the y values that are greater than that? They're up here, right? So that told me to shade this outer portion within the graph here. So again, you can always pick a point like 0, 0 to test it. You just can't pick a point that's on the graph. It's either got to be outside or inside the graph. So if I did pick 0, 0, 0 is greater than negative 1. That's true. So I know 0, 0 should be in my shaded area because it created a true statement. Okay. These you most likely have seen before as well. Typically we do these in Algebra 2. Same thing. You're just now doing a system of equations, right? What's what this chapter has all been about. So when you do a system of equations, we're just putting two graphs together. And ultimately what we're really looking for is where is the area that would be shaded by both graphs, right? Not just one of them. So we started out by just shading this parabola right here. So again, it's a parabola that was shifted down 1. It was dotted because there's no equal sign, so it looked like this. And this one, because it says y is greater than, would have been shaded all over this interior portion of the graph, right? And so that's what I did on this one, was I had shaded all this interior portion. Then I graphed the line, right? So here's the graph for the line. And where would he be shaded? This one says y is less than the line. So this one would have been shaded down in this area here. And so that's where I did the sideways shading, was below that line. Again, ultimately what you're looking for is where's the area shaded by both graphs. And this is where they overlapped, was this interior piece. So I made that one extra dark. Really, if you're doing this like in homework or something like that, this is what it should look like when you're done. We only want to see the shading for the overlap, right? The area that's shaded by both graphs, right? We shouldn't see this extra stuff that would get erased, so we don't make it look like it's part of our answer. Don't always assume that it's this interior piece that gets shaded when you're doing a system. That can change. Let me show you one. So here was a case where I graphed this parabola and this line. So the dark blue is the parabola, and the light blue is obviously the line, right? And here is, on this one, if we shaded this correctly, you can see that it's not the interior piece right here that got shaded, right? It was what you're seeing on this darker shaded portion right here. Let me take you quickly through what I did on this, because I wanted to take you back to our old school method of graphing here. So if I wasn't using a graphing calculator or Desmos, here's what you guys have learned in the past for how to graph parabolas like this. Remember, for these, the first thing that we're trying to figure out is where's the vertex. And so for the vertex, what we do is we figure out the x coordinate by doing this little formula that I know you guys remember, negative b over 2a, or it at least rings the bell. So if I did negative b over 2a, I come out with 1.5, and that's my x coordinate of my vertex. And if I take that number and plug it back in for x, here and here, then I get the y coordinate that goes with it. So that's where I came up with this point, the vertex. As far as figuring out more points on the graph, all I had to do was plug in 0 for x, which comes out to be -1. And I plotted that point right there at 0, -1. And remember, this would just mirror over the middle of the graph because parabolas are symmetric. So if the middle of my graph is right here at 1.5, well, any point that is 1.5 units to the left would also have a mirror point that is 1.5 units to the right. And that gave me the second point right here. And so then I just drew the curve. I kept it dotted because there's no equal sign involved. So as far as the line goes, just basic line stuff. I just got y by itself so that it looked like this. Don't forget, when you divide by a negative, it does flip your sign, so this became a greater than sign. So these were both greater than. The parabola was greater than, and the line was greater than, so both of them were being shaded in the upward direction. Okay, and so, again, I only kept the portion of my shading that belonged to both graphs. All right, so they both got shaded upward above, and so I'm only shading the piece that belongs to both. So let me take you through, so this is kind of where my video cut out, was when I was making this circle. So I wanted to show you this one because it's obviously a little bit different, graphing a circle. Now I know we've talked about these this year. Remember, x squared plus y squared equals r squared. So this fits the typical layout of our circle, of any circle. So for this, what I did was say, well, if 4 represents r squared, that must make the radius 2. And so from the center of 0, 0, I went 2 in every direction. So up 2, right 2, down 2, and left 2. Right? And so if I just connect the dots, I got my circle. With this one, it would be really hard to figure out where to shade it by the sort of the method of just looking at the symbol here. So what I did was I used the method of picking a point. So I took the point of 0, 0 and plugged it in, right? There's only two places I can shade this. It's either inside the circle or it's going to be outside the circle, right? So I picked 0, 0, plugged it in, and would that be true or false? So 4 is less than 0 is obviously a false statement. So that means I'm going to be shading this exterior portion of the circle. So it would all get shaded out here. I'm going to hold off on that because, again, I want to see what happens with the line that I graph right there. So as far as the line goes, y is greater than x. So remember, y equals x just means you're starting at 0, 0, you go up 1 over 1. So I know the line looks like this. And this guy's going to be dotted since there's no equal sign. So let's try to figure out the area that would be shaded by both graphs. This one is, so I already said the circle would be exterior, right? So which means I'm either going to shade this region or I'm going to shade this region right here. All right, it's going to be one of those two. So this one says greater than x, which means I'm looking to shade the area that's above that line. Again, you could pick a point, see if it fits, and then determine where to shade from there. So this one, if we shade it correctly, should be this exterior piece right here. This is the area that belongs to both graphs. All right. And again, if you ever wanted to test it to see if you did that right, pick a point within the shaded area, plug it into both equations, and it should make a true statement for both equations. So let me move down to this guy. All right, so for this example right here, so let me talk you through this example, and then we're going to do one together on this one. So the basic idea is we're given a function right here. This is they call this the objective function. So this is like the main set of values that we would be looking at, 3x plus 4y. However, they're saying this is not unlimited. There are some constraints to it. And so they're saying that within this little function, there are some general constraints given by these four inequalities right here. So these are limitations or constraints around this function right here. So what they did was they said, well, let's take a look at the graph. So if you were to graph all four of these, so y, basic lines here, so y minus x is less than or equal to 2. That was this guy. That's this line right here. The second equation that you see would be that line right there. You can see they do intersect at the point 2, 4. They also said that x has to be positive and y has to be positive. So with all four of these, if you were to graph all four and shade them, you would see that your shaded area is right here. So this is like the boundary section of our solution set. So our answers are limited to that section right there. Those are the constraints, right, of acting on this objective function right here. Guys, typically this is done within like a word problem, where the constraints end up being things that would be logical constraints. Like if I was talking about, say, something related to the area of a square. Let's say maybe the objective function had to do with like an area of a square, right? Or something along those lines, area of a rectangle, whatever. So some of the things that would naturally fall into those constraints are, well, if x and y represent my length and my width of the rectangle or the square, then what are some things that would have to limit my dimensions? Well, first of all, dimensions can't be negative, so your width and your length would both have to represent positive numbers, right? Things like that. So these would be natural constraints on that type of an objective function. So just to give you an idea of kind of usually where these go. But ultimately what they're asking for is, within our objective function, what is the maximum value and what is the minimum value limited by these constraints? So I can only look at the shaded area. So what would be my maximum and my minimum values within this shaded area, right, that are being acted on to this objective function? So here's what kind of the way this goes. What they're figuring out is, where are what they call the corner points, right? The corner points are sort of the extreme points within this. So you can see right here at 0, 0, 0, 2, 2, 4, and that was 4, 0, right? So those are my corner points. There's 4 of them. So those are the 4 extreme points within this graph. So that means our maximum and minimum values are gonna lie on those 4 points. One of those 4, 2 of those 4 points, right? Because those are the most extreme values within that diagram right there. So they said, well, let's test them, right? So if I plug in 0, 0 for x and y onto my original function up here, right, what would I get as my result? Right, the result would be 0. If you plugged in 0 for x and 2 for y into that objective function up there, this is the result that comes out of it. Here's my next corner point, came out to be 12. My next corner point came out to be 22. So if you look at those corner points, you can see that the smallest result within those constraints was 0. That's the minimum. And the maximum was 22. That was the largest result, and that's the one that came out of this point right here. Right, and so we would identify this as our minimum and this is our maximum. So let's do one of those together here. So we're going to kind of walk through this so you can see how this should go. All right, so for this one, here is our objective function, 2x minus 3y. So right here you are seeing the objective function, and then these 5, 6 graphs are the constraints acting upon it. So we got to start by graphing these guys and identifying where is the shaded area within those constraints. So let me just start with, I'm actually going to start with the easy ones. So x is greater than 0. That just would be our y-axis. So that's right here, right? And if it says greater than 0, remember that's pushing us to the right. So that would be the area to the right represents him. Y is greater than 0 would mean I'm now above the y-axis. So automatically I am now just by these two. I'm already limited to quadrant 1. I also have to be less than 5 for the y. 1, 2, 3, 4, 5. So I have to be below this line. And x is less than 5. 1, 2, 3, 4, 5. Means I got to be left of this line. So right now I'm looking at this little window of my constraints. Let's look at these two graphs. So this one starts at -4 and goes up 1 over 1. So if I was starting at -4 and went up 1 over 1, I know I would hit +4, up 1 over 1. So here is this graph. And then one more of these. So this one starts at 4, goes up 1 over 1. So this one starts at 4, goes up 1 over 1. All right, so you can see the little window, and if we were to look at the shading, so again, if you were to look at this one that I graphed, it's a greater than, so I know that one goes above that line. This one that I just did was a less than, so it needs to go below that line, right? And if I were to really go through all the shading of all 6 of these graphs, you can see that it basically gives me this little window right in here. Right, so this is the shaded area that would be true about all those graphs. So what they are asking me to do is to come up with the minimum and maximum values within that shaded area. So we always want to identify sort of those corner points within this. So we could even start right here at 0, 0. Right here I'm at 0, 4. Right here I'm at 1, 5. Over here, these guys intersected at 5, 5. And then down to this guy, which is 5, 1. And then lastly is 4, 0. Add that guy on. So those are all the corner points within that graph. So let's identify maximums and minimums by just simply plugging in these numbers into the objective function. So if I plugged in 0 for both, I would get 0. If I plugged in 0 for x and 4 for y, I would get -12. And let me just keep going down the list here. So let's see, that would be 2 minus 15. That would be 10 minus 15. 10 minus 3. And 8 minus 0. All right, so just by looking at those corner points, again, you can see my minimum value is right here at -13, and my maximum value within those constraints would be 8. It does say to identify the points where that takes on those values. So again, I would identify 4, 0 as the point that produces a maximum of 8, and 1, 5 is the point that produces a minimum of -13. So not too bad on those. So let me show you one last example out of your book along those lines. Pretty much the same deal that we were just looking at. This will be on page 552. I just wanted to show you how this came up within a word problem so we can interpret a little bit of what's going on here. So they're talking about purchasing fertilizer with 2 nutrients. So we got the nitrogen and phosphorus. There's our two items within our bags of fertilizer here. So start looking at some of these phrases as we go through this, because these are going to produce the constraints within our function here. So if it, meaning the bag of fertilizer, needs at least 180 units of N and 90 units of P, so we'll get to that in a second. 2 brands of fertilizer. So here's where the variables are going to come in. So brand A, you'll notice that they're going to call that X, right? So the X's are going to represent the number of bags for brand A. And in brand A, for one thing that we need to identify as a total is it costs $10 a bag. And Notice that within a bag, there is 4 N's to 1 P, right? So so for brand A bags, right, it's 4 nitrogens to 1 phosphorus, whereas the brand B bags, which is going to be our Y variable, you're looking at 1 of each, right? So if I get some, I'm going to get some amount of X, which is brand A, plus some amount of Y, which is brand B. But look at the relationship of nitrogen from brand A to brand B. There's a 4 to 1 ratio there. So if I get some amount of brand A, I'm going to have 4 times the nitrogens than I would for brand B. So I'm trying to hit on that because the constraints on this one I thought were just a little tricky and a little confusing. So let's look at the constraints that they're setting up here. So it said for the nitrogen we needed at least 180 for nitrogen, right? So I'm going to have some amount of brand A, that's X, plus some amount of brand B, which is Y. Has to be at least 180 nitrogens. So notice that they're using that 4 to 1 ratio right here because there was 4 times as many nitrogen in brand A as there was in brand B. It's not just like I can get some total of both and they're both equal. Okay, so that's where the 4 to 1 relationship is coming in. However, when it came to the phosphorus from brand A to brand B, they both had a 1 to 1 relationship from brand A to brand B. And so that's why it's 1x plus 1y is going to give me greater than or equal to 90 as far as the phosphorus is concerned. They said that it's got to be less than $800. So there's our total cost as we're looking at those. And so look at the 10 and the 5 relationship on that. Remember the comparison from brand A to brand B. Brand A was $10 for cost. Brand B was $5, right? And it's got to be at most $800 total. And so that's where they're getting that third equation that you see right there. And then obviously they're saying you have to get at least some amount of A and at least some amount of brand B. And so that's why they both have to be greater than 0. So that we're buying at least some of both. So those are the 4 constraints. From there, that's the hardest part, I think, is just identifying all the constraints. Because from there, it becomes exactly like what we just did in the previous problem. Right? You would graph those. You would find the shaded area that belongs to all of those. So you can see the sort of the restricted area of that graph. There's only 3 corner points to identify. So right there, they identified one. And you can do all this on calculator right there, and you can do it right there, right? So we're solving that system of equations for all those 3 corner points. So they went on to test them like we did on the previous problem. So these were the 3 corner points that we just identified. You can see the results that come out of that. So the way that we would interpret that is, and obviously ultimately when we're talking about cost, I want to spend as little as possible. So we were looking for where I could get everything that I needed for the smallest cost possible. And so you can see that right here at this 3060 is where I'm going to get the smallest cost out of those 3 corner points. Right? And so here's where they go on to explain, okay, so what are we looking at then? Well, the minimum cost is going to be $600 when I get 30 bags of brand A and 60 bags of brand B. Right? And because we already identified the constraints and all this stuff within the graph, we know it's fulfilling the requirements that was laid out for us within the problem, right? If we use 30 and 60, right? And so anyway, so that's how it gets used within the problem. A little tougher when it gets to the word problems as far as identifying the constraints, but that's really the only extra piece that you're seeing on this one. But that is it for this chapter.